Hello everyone, and welcome to some more remote learning. I'm the tutor in the math help room, and today I'm just going to introduce you really quickly to power series and then go in polynomial approximation of functions. So, the quick introduction of a power series. The general form of our power series is going to be some constant c sub k times x minus a all raised to the k. Now x is our variable, so if I was to write out a few of these terms, for example, plugging in k equals 0, then I'm going to have c sub 0, so some constant, times x minus whatever a is, all raised to the 0. But think about something raised to the 0 is going to be 1. So c sub 0 will be multiplied by 1. And then I'll be adding that to c sub 1 times x minus a to the 1, which is just x minus a, plus c sub 2 times x minus a squared, and so on. So you can see that here we have a degree of 0, whereas this is a polynomial with a degree of 1. And then if we go up to where it's squared, that's a degree of 2. And we could go up to n, so c sub n times x minus a to the n, so that would be an nth degree, but we're going towards infinity, so then that would continue on. And this is just the general form for how our power series is laid out. The powers of x change, hence a power series. But this is just a quick introduction, and I'm going to build on this and come back to this a little bit later in this worksheet and in a different lesson. So let's jump into actually approximating some function now. Think about ln. How would we approximate the ln of 1.1? Well, if you dig back into your Calc1 knowledge, we've done linear approximations before. And the formula for a linear approximation is f of a plus f prime of a times x minus a. That's our linear approximation of some value. And how we build upon this linear approximation is we take a value that's easy to find within our function. So ln of 1.1, a value that's easy, that we know right off the top of our heads, is the ln of 1. The ln of 1 is equal to 0. Right? That's something we know. So what we're going to do, what this equation does, is it simply takes that tangent line at the point and moves along the tangent line to estimate the next point, as opposed to moving along the function. So with that being said, the a value we're choosing, or we're centering around in this case, is going to be 1, because we know the ln of 1. So let me rewrite this in a different manner. So I'm going to say that a is going to be equal to 1. So f of a is going to be the ln of 1, and we're going to add that to, well, the derivative of our function at a, which if f of x is equal to ln of x, then the derivative f prime of x is going to be 1 over x. But remember, we're taking the derivative of our function at some point a, so we're going to be plugging in 1 for a. So f prime of a, or f prime of 1, is going to equal 1 over plugging in 1 for x. That'll be 1. So we're going to add that to 1 times x minus a, which is x minus 1. So this is our linear approximation. If I was to draw this out quickly, here's what our ln function looks like, and here is the point 1, because the ln of 1 is 0. Now what I've just done is I've taken this value and I found the tangent line, or the slope of the tangent line, and I'm moving along it a change of x minus 1. So if we're calculating this at 1.1, I'm going to have the ln of 1, which is 0, plus 1 times 1.1, plugging that in for x, minus 1. Well, that's going to be 1 times 0.1, right? Because 1.1 minus 1 is equal to 0.1, and 1 times 0.1 is 0.1. So our approximation for the ln of 1.1 is 0.1. But that's not us moving along the function. That was us taking the slope of our tangent line into account and moving along that tangent line, which is very close to the value of our function. And you can kind of see that visually. Now, linear approximation is great when we're really close to our actual value. So 1.1 is fairly close to 1. But if we wanted an even more accurate estimation or an accurate approximation, we would move from a degree of 1 or a linear approximation to a quadratic approximation, so a degree of 2. So our quadratic approximation is built by our linear approximation, which is f of a plus f prime of a times x minus a. So here was our degree of 1, but we're going to add on something to a second degree. And that's going to be the second derivative, so f double prime of a all over 2, or this is really a 2 factorial that's equivalent to 2. So I'll write it as 2 times x minus a squared. Now this formula is derived in your book, and you can find proofs for it on the internet. So I'm not going to go into the basis of this formula, just know that this is how you do a quadratic approximation. So we have our linear approximation from up above, but what's missing now is we have to find our second derivative of a, and I'm still going to be approximating 1.1. So I'll simply rewrite f of x is the ln of x. And we know that f prime of x was equal to 1 over x, or x to the negative 1. So if we take the derivative of f prime of x, that would be f double prime of x, which is going to be negative 1 over x squared. Now for us, since we're plugging in an a value of 1, that's just going to be a negative 1 for that derivative, filling in all my parts. So let me write this out really quickly. So f of a is the ln of 1 plus our f prime of a, which is 1 over 1, times x minus 1 to the first, plus f double prime of a, which is negative 1 over 1 squared, that's all over 2, times x minus 1 squared. So we'll get the ln of 1, which is 0, plus 1 times x minus 1, plus this comes out to be a negative 1/2 times x minus 1 squared. And the x we're plugging in is that x value we're trying to approximate, and that's going to be 1.1. So we'll have 1 times 1.1 minus 1 plus negative 1/2 times 1.1 minus 1 squared. Well, we know our linear approximation chunk was just 0.1, so that's going to be 0.1 plus 0.1 squared is going to be 0.01, and we're going to be multiplying that by a negative 1/2, which is negative 0.005. So we'll have 0.1 plus or minus 0.005. So our quadratic approximation of 1.1 is 0.095. Now that's a closer approximation than 0.1 for our linear approximation above. So we're getting closer to the actual value of the ln of 1.1. So we did a polynomial approximation of a degree of 1. We've done a polynomial approximation of a degree of 2, but we can continue this on and do more polynomial approximations to different degrees. And polynomial approximations based on derivatives of functions are known as Taylor polynomials. Diving into our definition of Taylor polynomials, it says let f be a function that can be differentiated n times at x equals a. The nth order Taylor polynomial about x equals a is in the form of this. P sub n of x is equal to f of a plus f prime of a times x minus a plus f double prime of a over 2 factorial times x minus a squared plus f triple prime of a over 3 factorial times x minus a cubed, and so on, continuing to add those terms up until the nth derivative of a over n factorial times x minus a to the n. So Taylor polynomials are really neat because they allow us to take some function. In this case, for the example in the worksheet that I'm going to be doing, is going to be the ln function. But Taylor polynomials allow us to take other functions and approximate them based on simple arithmetic operations. So addition, subtraction, multiplication, and division. That's what a Taylor polynomial allows us to do, to take some function like the ln and rewrite it with simple arithmetic operations. So if I was to write this in sigma notation, this is going to be the summation of k equals 0 to n of the kth derivative of a all over k factorial times x minus a to the k. So you notice that when we go up to n, we're plugging in n and we'll get this. Now why I introduced power series up above was to show you some sort of resemblance. We're eventually going to extend this concept or expand upon this concept in later lessons to create Taylor series, which is a type of power series. And if you notice, if we were to rewrite this as opposed to going to n, we went to infinity, this is like our c sub k term. So if we change this from going to some value of n and went up to infinity, then this would be known as a Taylor series as opposed to some nth order Taylor polynomial. It would be known as a Taylor series, which is a specific type of power series. So you can see that kth derivative of a over k factorial is that constant c sub k from up above. So scrolling back up, if we took this towards infinity, you see that we have our c sub k, which we defined in our Taylor polynomials. There's a minus a to the k, but just for this worksheet, we're not going to infinity, we're just going to n. But hopefully you can see that relationship and then be able to build upon it in our later lesson. But for now, let's just focus on these Taylor polynomials to some nth degree. So for this example in this worksheet, we're going to be finding the nth order Taylor polynomial of the function f of x equals the ln of x centered at x equals 1. So a, in this case, is equal to 1. That's what it means to be centered at x equals 1, is that a is equivalent to 1. And we're going to do this for a degree of 0, 1, 2, 3, 4, and 5. But from above, I've kind of helped you build into this because we've already done 0, 1, and 2. Remember, so filling in this table, our function is that ln of x. Remember, our function, we're going to be centering that at x equals 1, which means that a is equal to 1. So plugging in 1, we'll get the ln of 1, which equals 0. So p sub 0 of x is going to be equal to 0. Now, from up above, if you remember from our linear approximation, the derivative of ln of x is 1 over x, which some of you may like to think of as x to the negative 1. Now when I plug in our a value for this, I get 1 over 1, which is equal to 1. So my first degree Taylor polynomial, which was my linear approximation, is going to be my p sub 0, which was 0, plus my f prime of a times x minus a, which a was 1, to that first degree, or to the 1. So now when I build my p sub 2, I need that second derivative, which is negative 1x to the negative 2, or negative 1 over x squared. So negative 1 over 1 squared is going to be a negative 1. Now when I'm building my second degree Taylor polynomial, I need to take everything from my first one, which included terms from my 0. I'm going to take p sub 1 and add it to my new chunk. So p sub 1 was 0 plus 1 times x minus 1, and I'm going to be adding that to my second derivative, which was a negative 1. So as opposed to adding, I'll subtract 1 over 2 factorial, which is 2, times x minus 1, x minus a, squared. That's my second degree Taylor polynomial. Now, just to help us out a little bit with consolidating and simplifying, I'm going to make a dashed line here, and so that we can simplify as we go along, I'm going to make this our nth derivative of a all over in factorial, just to help us simplify it down, because remember that's like our c sub k, so that's what's going to be multiplied by x minus a to the n. Because remember, p sub n of x is going to be equal to the summation from k equals 0 to n of the nth derivative of a all over in factorial, and that was times x minus a to the n. So quickly, filling in those spots we've missed, 0 over 0 factorial, well, 0 factorial is 1, so that's where we got 0 from, because 0 divided by 1 is 0. And then 1 over 1 factorial, that's going to be 1. And then we got a negative 1 over 2 factorial, so that's where we got negative 1/2. Now let's go ahead and do our third degree approximation. So this would be negative 1 times negative 2, which is a positive 2x to the negative 3, which is going to be equal to 2 over x cubed. And 2 over 1 cubed is 2. So now when we do this, we're going to have 2 over 3 factorial. And 3 factorial is 3 times 2 times 1, which is 6. And 2 over 6 is going to be equal to a positive 1/3. So our p sub 3, our third degree polynomial approximation, or our third degree Taylor polynomial, is going to be all of p sub 2. So we're going to have 0 plus 1 times x minus 1 minus 1/2 times x minus 1 squared plus 1/3 times x minus 1 cubed. Now let's go ahead and do our fourth degree approximation. So taking the derivative of 2x to the negative third, that's going to be negative 6x to the negative fourth, or negative 6 over x to the fourth. And remember, we're plugging in 1 for that, so that's negative 6 over 1 to the fourth, which is a negative 6. Now, we'll take that derivative at a, negative 6, and put it over 4 factorial. And 4 factorial is going to be 4 times 3 times 2 times 1, 24. But negative 6 over 24, I can simplify down as negative 1/4. So we'll have negative 1 over 4. So our fourth degree Taylor polynomial is going to be all of p sub 3 plus our new c sub k chunk times x minus 1 to the fourth. So our c sub 4 times x minus a to the fourth. So that's going to be 0 plus 1 times x minus 1 minus 1/2 times x minus 1 squared plus 1/3 times x minus 1 cubed minus, because this is a negative, so we'll have minus 1/4 times x minus 1 to the fourth. Now if we were to do this to an n value of 5, we'll get negative 6 times negative 4, which is 24x to the negative fifth, which is equal to 24 over x to the fifth. And 24 over 1 to the fifth is going to be equal to 24. Now when I place this 24, so that's my fifth derivative at a, when I put that over 5 factorial is going to be equal to 120. And 24 divided by 120 simplifies down to be a positive 1/5. So for my fifth degree Taylor polynomial, I'll have all of what I had in p sub 4, so I'm just going to rewrite p sub 4 to save space, plus I'm going to have now 1/5 times x minus a, or x minus 1 to the fifth. So now let's go ahead and approximate that ln of 1.1 with each of our different polynomials we found in part A, because then you're going to see they're going to get more and more accurate. So if I make a new column, I'll say p sub n of 1.1, because that's the x value I'm plugging in. So obviously we're going to get 0 for our approximation of 1.1 when we're doing a degree of 0. But if we remember our linear approximation from above, when we plugged in 1.1 for x, we got 1.1 minus 1, which was 0.1 times 1, so this is where we got 0.1. And then from our second degree, or our quadratic approximation, if you remember, we've got 0.095. So we're going to take that 0.095, which is this, and then we're going to add it to 1/3 times 1.1 minus 1 cubed, which is 0.0003 repeating. And when we add that to our p sub 2, we get 0.0953 repeating. So you can see we're getting even closer. So feel free to do these other two out on your calculator, but I'm going to skip on to C for the sake of time. So we're going to write this Taylor polynomial in sigma notation. Now, because when we had a degree of 0, that term was 0, as opposed to starting at k equals 0, I'm going to start at k equals 1. And we're going to go up to sum n. Now, in each of these terms, we have x minus a, which is x minus 1, and the degree of that increases along with k. So every term has an x minus 1 to the k. Now, the only other thing that this term has is like our c sub k component. So 1, -1/2, 1/3, -1/4, 1/5, and then I can assume the next term would be -1/6, and so on. So it might be actually easier to look at those in this column here. 1, -1/2, 1/3, -1/4, and 1/5. So finding that pattern, we're going to have 1 over k. So we have some 1 over k, but not just a positive 1 every time. Note that our series alternates. It goes from positive to negative to positive to negative. So we have to have some -1 to the k over k. However, if I plug in 1 for the first term, I want it to be positive. And when I plug in 1 in my summation as of now, it's negative. So all I have to do for this is to add 1 to k in this instance. So now you can see when I plug in a positive 1, I get -1 squared, which is positive 1 over 1. There's my 1. And then when I plug in a k value of 2, I get -1 to the 2 plus 1, which is -1 cubed, which will be -1 over 2. So that should be our -1/2. Plugging in 3, I'll get a positive 1 over 3. Plugging in 4, I'll get a -1 over 4, and so on. So this is our pattern in sigma notation. -1 to the k plus 1 times x minus 1 to the k, all over k. Now I think where the real understanding of the power of Taylor polynomials comes into play is when we look at how we're building that graph and becoming more and more accurate with our approximations. So let's go ahead and pull up Desmos so that we can see this in action. Now I have this linked so I can put it in my video description, and you can see from here I have my function f of x equals the ln of x, and we're centering around an a value. P sub 0 of x is just going to be f of 1, which we calculated to be 0. So when I click on this to show the graph, you can see that blue line pops up. But what I really want to look at is going to be my first degree approximation. So that's my P sub 0 plus f prime of a times x minus a, which there's that tangent line that I showed. Then if I did my second degree approximation, notice how we get a little more accurate. It's hugging our function a little bit closer around that point we're centered around. And then a third degree approximation is even closer. Let's go ahead and zoom in so we can see this a little bit better. So I'll get rid of my first degree because my second degree was more accurate than that. So you can see centered around that point of 1. And then let's get rid of that second degree, and let's look now at our fourth degree. It's even closer. It's hugging the graph even tighter. And then moving on from that fourth degree, let's look at that fifth degree approximation. It's even closer. So you can envision taking this to the 6th degree, 7th degree, and so on. It's going to get more accurate to that value we're trying to approximate around. Now, because I skipped over actually estimating the ln of 1.1 within our 4th degree and 5th degree Taylor polynomials, notice that I've already done this down here. P sub 1, we got 0.1. P sub 2, we got 0.095, and then for p sub 3, when we calculated that together, we got 0.0953 repeating. And then if we continue to p sub 4, we would have calculated it to be 0.095308. And then let's go ahead and enter in p sub 5 of our x value we're estimating. That's 0.09531. So you can see we're getting more and more accurate, and our original function value, which I also calculated in this table, is 0.0953118. So you can see each of these values gets closer and closer. And let's quickly type in that summation. So if you remember our Taylor polynomial and sigma notation, we had the summation from n equals, I'm going to change this from n, I want to do a k value from, we started at 1 in this case, up to some value n, and we had -1 to the k plus 1, all times x minus a, which, because I have a already defined, it's going to fill that a value in, and that's to the k, all over k. Now I'm going to add my slider in, because what I went from is we started at a first degree approximation and we went all the way up to a fifth degree approximation. So I'll go ahead and step this through. And I'm going to change this to be the dotted black line. So the dotted line is our sigma notation representation. So you can see when we go to a degree of 1, it's going to match our first degree approximation. So if I click our first degree, second degree Taylor polynomial, third, fourth, and fifth, note that as I slide our n value along, right now I'm at that first degree Taylor polynomial approximation. Now my line follows our second degree approximation, then it matches the third, then the fourth, and then you can see it'll follow the fifth. And I can continue this on if I stepped in up. Let's go to, say, a Taylor polynomial of 10. That's just going to become more and more accurate about where it's centered around. So again, these Taylor polynomials allow us to take some function that's hard to compute mathematically, but then we write it as simple arithmetic operations: addition, subtraction, multiplication, and division. We took that ln function and are able to approximate it using basic math operations, which I think is really neat. So feel free to fill in our fourth degree approximation and fifth degree approximations, showing how it becomes closer to that actual value of the ln of 1.1, which was 0.0953118. So hopefully walking through this example gave you a little bit more of an understanding of Taylor polynomials, and we'll expand upon this in later lessons and in later examples. So in a later video, I'll dive in, expanding upon Taylor polynomials, going into Taylor series, which we said was a subset of power series. And then we'll go even further into those Taylor series, going into a subset of that, which is a Maclaurin series. So stay tuned and get ready for the next video.